Hello, chemistry people. Welcome to a freezing day in the lab in Melbourne. And today I have IBSL chemistry topic 4.1, which is all about ionic bonding. Something that could be helpful with this is if you grab a periodic table. So while you do that, I am just going to set up so I can take some notes for us. Okay, so as always, I don't know why it's saying I'm not signed in, but I am still Amy. So let's have a look at our study guide. So we are going to talk about cations and anions, how that relates to electron gain and loss, what ionic bonding are, and what ionic compounds are. We're going to talk about how we work out names, including the polyatomic ions, and we're going to link structure to physical properties. And we've got some memory work at the end. So when we look at anions and cations, it's probably easiest for us to think about our periodic table and just a very sketchy version. Our metals are what are going to be losing electrons. So if you minus a minus charge, you end up with a positive charge. So these are our cations. Over here, we're going to have our negatively charged ions, and note there that I am not highlighting our noble gases. So in here, my non-metals, I'm going to be gaining electrons, which means, so if you add a negative charge, you're going to end up with a minus charge. So these are our anions. So how that works in terms of electron structures. So if you think about sodium with one electron in its outer shell, and chlorine, I'm actually going to do crosses here. Chlorine with 7 electrons. This sodium electron gets stolen by chlorine for reasons that we discussed in the periodicity topic. So once that electron is gone from the sodium, this ends up with a positive charge because it's lost a minus. And now my chlorine atom has an extra electron, which makes it a chloride ion. These guys all have very predictable names when they become anions. So chlorine becomes chloride, fluorine becomes fluoride, and you get absolutely 0 points. It is Eurovision time, so of course I'm thinking in terms of points. You get 0 points for knowing that iodine becomes the iodide ion. Similarly, oxygen becomes oxide. Okay, so those are a quick, rough introduction to those, because in a lot of cases you will have done ionic bonding in previous years of high school. This in and of itself does not feature heavily in mark schemes, but you do need to know that a positive charged ion is called a cation, and a negatively charged ion is called an anion. So periodic table to electron config to ion charge. So let's go back to this sketch that, oh, that would be nice if I could draw a straight line. Let's roughly draw out a periodic table, just like I did before. So the goal, if you are any sort of atom, is to get an electron structure, that looks like a noble gas. This is the goal. So if you are a metal, particularly one in these two columns, you are either going to lose 1 electron or 2 electrons in order to get that goal. If you are, and I'm going to pick a different color, if you're one of these guys, you are going to gain 1 electron or gain 2 electrons if you're oxygen or sulfur, or even if you're nitrogen, gain 3 electrons. Carbon is special because carbon pretty much only does covalent bonding. But the periodic table can tell us the electron config. We discussed that in periodicity and atomic theory. But from there, we can also work out the charge that an ion will have. Okay, so once I've formed a sodium and a chloride, so let's say that my sodiums are, what color do I want to make sodium? Let's make sodium blue and chloride green. So sodium, so ionic crystals have a very distinct shape. Now there are things called coordination number. That is not something that we need to know in the IB. So we have an alternating pattern of positive and negative charges. And this is a 3D structure of positive and negative ions. This thing here is called a lattice. So sodium chloride has a melting point of 801 degrees C, according to Google. And that is because of the incredibly strong attractions between the positive and negative charges in my lattice. This lattice is brittle. So if I have a lump of rock salt and I hit it with a hammer, it shatters apart instead of bending. And the reason for that, if I'm careful, I should be able to do this. So if I hit this lattice and displace this row of ions down, what I've now got is a repulsion. Let me see if I can do this here. I've got repulsions between these ions, which means that my lattice will break apart. Okay, so let's put my ions back the way they were. When I hit this with a hammer, my ions move, and then these guys will repel apart. That's why these are brittle. Now, solubility in water. I didn't mean to do that. There we go. So solubility in water. It's actually really quite cool. So water, for reasons that we get into in a later topic, has a slightly negative end and a slightly positive end. So what happens, am I able to rotate? No. So when I put my salt crystal in water, the negative ends of my water are attracted to my positive sodium ions, and my positive hydrogens are attracted to my negative chloride ions. What that does is my water picks up my ions and drags them apart. If I do this process enough times, I end up breaking apart this lattice. That's what dissolving is. It's where my water molecule attracts itself onto an ion and picks it up and moves it. That's what solubility is. Now, these things don't conduct heat terribly well. I don't know if you've got or if you've ever seen the Himalayan salt lamps. I don't know what their purpose is, but they are a large chunk of salt that people put light globes in. Now, they do warm up, they just don't do it much. And that's because these particles, because those electrostatic forces are quite strong, those particles don't really move within that lattice to a great degree to pass on that heat. Now, for electrical conductivity, I need to explain why things conduct electricity. So let me do a little sidebar here in my beautiful orange pen. So in order for something to conduct electricity, I need to check two boxes. I need my substance to have charged particles. And I need those particles to be freely moving. Okay, so if I have charged particles that are freely moving, I have something that can conduct electricity. So let's start by looking at this lattice as a solid. I have charged particles. I've got my cations and my anions, but those charges are locked into that lattice. They can't go anywhere. So this thing has the charged particles, but it doesn't have them moving. That means that this is not going to conduct electricity. However, if I melt this or dissolve it in water, I'm going to pause. I'm going to do something quickly. Okay, so now that I have either melted or dissolved those ions, it could be either based on the way I've drawn it. Now that I've broken that lattice, these ions are able to move inside my container. So in this beaker, I have charged particles that are able to move. Now that ticks both of my boxes. So now that I've ticked both of those boxes, this is why salt water conducts electricity, but a piece of rock salt doesn't. Okay. So going from names to formulae and formulae to names, we always name cation, then anion. Anion. So you're always naming, generally speaking, the metal, then the non-metal. The other thing you need to be able to do is identify the charge on an ion based on what it's attached to. So if I have an unknown metal attached to two chloride ions, each of those chloride ions has a -1 charge. So this guy must have a +2 charge. So this is a common multiple choice question where they will say a metal salt has the formula XCl2. What would be which of these following ions has the, which of these following ionic compounds has the correct structure? So it might be like XNO3, SO4, XOH3 XPO4. And you've got to choose which one of those has the correct formula. Now, all of those ions I picked, ta-da, are the required polyatomic ions. You need to know the names of those, which I will write in just a minute. But these two often work together. So in order to work out the names of things, some of them are these required. So let's talk these through. So NH4 plus is ammonium. OH minus is hydroxide. NO3 1 minus is nitrate. HCO3 minus is hydrogen carbonate. CO3 2 minus is carbonate. SO4 2 minus is sulfate. You can also write that with a pH. And you've got PO4 3 minus, which is phosphate. So if I give you the name, if I give you the name sodium phosphate, you should be able to determine the formula from that name. So you start by identifying what the sodium ion is and what the phosphate ion is. Now, overall, I need to combine these in such a way that my charge ends up being 0 overall. The easiest way to do that is cross multiply. So this ends up being Na3 PO4. The only time you don't cross multiply is if those two numbers are the same, where you don't need to. So let's do another example of this. Let's do aluminium oxide. So aluminium is a metal. It is in the third block across on its period. So it forms an Al3 plus ion. Oxide, this follows the same naming convention as our halogen. So this is an oxygen ion. So oxygen needs to gain 2 electrons to get a full outer shell. So it's 2 minus. So these are different numbers. So we cross multiply. And we end up with Al2O3. Oh, sorry, I tried to make that clear and I just ended up. So that's Al2O3. Let's do an example where the numbers are the same. So let's do magnesium sulfate. So magnesium is in group 2, so it forms a 2 plus ion. Sulfate, you have been asked to remember, which is 2 minus. These have the same number, so I don't need to cross multiply. So it's just MgSO4. Okay, that is how we go from formula to names and names to formula. You need these polyatomic ions to do that though. So let's double check the study guide. We have talked about cations being formed by metals losing valence electrons and anions forming by nonmetals gaining electrons. We've talked about number of electrons linking to electron config, and we've talked about electrostatic attraction. Ionic solids are usually, ionic compounds are usually solids. I didn't actually specify that, but I did specify that they have high melting points. So I'm going to say that. Deduction of the formula and name of an ionic compound from its component ions, including polyatomic. We've just discussed that. We've talked about electrical conductivity and solubility. We didn't talk about volatility. So volatility is basically low boiling point. So if we have specified that our ionic compounds have a high melting point, it follows that they're also going to have a high boiling point. So a container of salt doesn't actually smell. There aren't compounds in that we can smell, whereas there are compounds, if we look at covalently bonded molecules, we can smell those, and that is because of their volatility. And we've talked about those polyatomic ions. So that brings us to the end. Thank you so much and have a fantastic rest of your day. And I shall see you next time. Bye.